Okay, so at this point, I have given you a link to this version of an EDAPlayground, and you can copy this into your workspace and modify it from there so you don't have to do quite as much typing, especially with the test benches. All right, so let's start with a review. Looking at the design side, I've put in all the includes for you, but notice Lab2 top.sv is missing. You'll have to add that file in. And Lab2 wrapper.sv is missing. So at this point, I'm wanting you to go ahead and start from a blank screen here and put in the module definitions for Lab2 top and Lab2 wrapper based on the schematic. If you get stuck on that, you can take a look at your Lab 1 results, and it's very similar. I think you'll be fine with that once you get started with the module definitions and instantiations and knowing how to do that. Okay, so add those two files into this design, and from there we're going to use a test bench to test various components of the design. So the one you don't have to worry about is the multiplexer design. That was just given to you, but we're going to do a test bench for Lab2 top, a test bench for Boolean 1, and a test bench for Boolean 2. All right, so let's take a quick look into Boolean 2. This is the exclusive OR. Use the Shift 6 to get this caret key. All right, and this gives you exclusive OR. And then, we had the module definitions with the inputs and outputs. And then Boolean 1, we have the module definitions with the inputs and outputs. Okay, so we have this all set up. All right, so the main thing that I wanted to talk about, though, in this video is looking at the test benches. All right, so over here on the test bench tab, you can use comment lines to choose which test bench you want to actually implement. Okay, so this design doesn't work because I don't have a Lab 2. That's not supposed to be there. Let's remove that. You're going to add Lab2 top and you're going to add Lab2 wrapper. And so this design doesn't work until you add those in. But once you get those added in, you can take a look at the Boolean functions. All right, so we talked a little bit about this in class. All right, so the main things I want to walk you through are the elements that show up in a test bench. Okay, so first element, you make a module name. All right, you also put this timescale directive in there to get everything on the same timescale. But you make a module name, and I just used the name of the module that we're trying to test, Boolean 1, and then added TB for test bench. It doesn't have any ports, all right? So you just write that and move on. Next, I use reg to control inputs, all right? So I have 3 inputs to this circuit. If you go back and look at Boolean 1, it had A, B, and C, and then it had an output F. All right, so F, the output would be a wire. All right, so let's review. We start with the module name. We define the inputs as reg, the outputs as wires. Then we need to instantiate the design. Okay, I use the label UUT. You can use B1, which is what I had in the diagram. That part doesn't matter. The label, it just has to be unique. All right. So then I had inputs A, B, and C, and the design has inputs A, B, and C. So dot A maps to A, dot B maps to B, dot C maps to C, and the output F, dot F maps to F. All right. So I set that up exactly the same way I've done all the instantiations so far when I've done Verilog. Okay, so the difference between the design side and the test bench side is test benches look a lot more like regular programming. Okay, there are some differences, but it's a lot like it, as you see here in a second. Okay, so the first thing I'm going to do is I'm going to use an integer I for Boolean 1, and then the next feature of a test bench is always going to be there should be an initial block. Okay, so I type the keyword initial, and then if there's more than one line, which there almost always will be, I need a begin and an end. Okay, So I'm going to begin the simulation and then I'm going to end it. All right, and along the way, when I'm done, there's a compiler directive that says finish, and that terminates the simulation so you don't have to wait for it to time out. If you forget to put the finish directive in there, sometimes it takes a long time for the simulation to run. Okay, so next I have put in here the command that you need to grab signals so that you can look at it in the EPWave program. All right, so from there, we're going to loop through all the combinations of A, B, and C. So I write a for loop, and it looks a lot like C++. All right, so you have this syntax. You can't use the I++, but you can say I is equal to I plus 1. Just like with the initial block, because it's more than one line, you need to enclose this between begin and end. All right, so I've got this begin block, and it ends here. All right, so I'm going to loop through I equals 0. I'm going to set A, B, C equal to I. All right, okay, and so, you know, you probably could be a little more prescriptive there and tell it, you know, that's supposed to be 3 bits, so 2 down to 0. I think it properly casts that, but this would be more correct. Okay. Don't worry about it. You can use it. It works the way it's written. So, all right. Then this input combination was specified. I then need to add simulation ticks. All right, so I'm going to wait 20 simulation ticks. It says wait for 20 nanoseconds in the comment here, and that's because we have this set up as the time scale. The simulation ticks are nanoseconds. All right, but don't worry about that either. Just think of it as simulation ticks. All right. The other thing that I've added in here is a compiler directive that lets you show results cast back to the screen. Okay, so this will show up in both the EDAPlayground screen and it'll show up in the Vivado console screen. All right, so this display directive, this looks a lot like printf. All right, so what you do here is you put between parentheses, you put some quotes, double quotes, and then I have ABC is equal to, and then %B just means binary, %B, %B, %B. So I'll get the 3 binary bits for A, B, and C. You know, those are the next thing in the list. And then F is equal to %B, that maps over into there. All right, so I'll pull this up here in a second and run it and you can see it. All right, so that's the first test bench. All right, we can look at the second test bench, which I did in a slightly different way. All right, it's the same kind of thing. Remember our steps. We instantiate the module. It doesn't have any ports. We put down the inputs. In this case, it's X, Y, W, X, and Y. Those can be on the same line because they're the same size. I like to do it 2 different ways so you can see it in different ways. The output is a wire. Then I instantiate the design. W maps to W, X maps to X, Y maps to Y, G maps to G. That's very common in test benches where everything's got the same variable names. Okay, then I start my initial block. It's more than one line, so I need a begin and I need an end. All right, I also have this compiler directive to finish things at the end. All right, so from here, you know, I had this comment in here. That's not that important, but I put an initial wait. That you don't need that. You could have just started right away. Okay, but this will run as it is, so you don't have to change it. All right, so from here, I put in all the input combinations with a line at the, or a #20 at the end to give me the simulation delay time. All right, so I just go through all the combinations. So it's like the for loop, only it's unwrapped. All right, so, you know, maybe I should have showed you that one first because I think that's easier to understand. You do this, and then you do this, and then you do this. You get the idea. With this approach, you let the loop take care of that. All right, which is great especially if you had, say, 5 or 6 variables, you're gonna, it would take a long time to type out all this for all the combinations. Okay, so that's 2 of the test benches, and the third one is for our top. All right, so that's a little more complicated because it has more inputs. So let's go through our steps. Instantiate the module. All right, so module Lab2 top TB for test bench. Put reg values for the inputs. So I have reg, x is a vector in this case, reg select line is a scalar, and then I have a wire for the output. Okay, then I instantiate Lab2 top. So I look at Lab2 top. I don't have that yet because you're writing that, but I look at that and I know that x is the input, select is an input, and f out is an input. All right, you can get that from the schematic. All right, as before, I define an integer I start an initial loop, I have a begin, I have an end. All right, and then what I'm going to do is I'm going to go through both combinations. The first thing I'm going to do is make the select line be 0. I'm going to start with an initial value of x being, and this is the notation for inputs of vectors in Verilog, where I say this is 3 bits. This the B part here tells it it's bits, not decimal or hex, and I just give the bit pattern at that point. Okay, so from there, I'm going to loop through the counter. So I'm going to go from I equals 0 to 8, strictly less than 8, so that goes to 0 to 7. It'll loop through and it will assign the vector x, the I, the 3 bits of I. All right. After each assignment, I wait 20 simulation ticks. All right, so that will give me all the input combinations for one of the Boolean functions. And then I change this to select equal 1. And then I do the same thing because with select equal 1, I should get the second Boolean function. Okay, so at this point, I'm going to go to a completed playground. All right. I'm going to first save this one. Okay, and go to the completed playground. All right, so on this one, I've added in Lab2 wrapper and Lab2 top. All right, so what I could do is run this, and I need to check on this to open the EP wave after the run. Okay, so, well, first I'm going to check without it. All right. And then I also need to select which Boolean function or which thing I'm going to test. All right, so my first one, I have this in here twice. The first one I'm going to check, I'm going to run the test bench for Boolean 1. So I've commented out the other test benches. So I can run this, save this, and run it. Okay, so remember I had that display command. Okay, so this is what echoed back to the screen. And you see that's convenient. That lets me explicitly see whether or not that logic function was correctly tabulated. And you can use your expected results table to verify that you got the right answer. Okay, then I'm going to also run it again and let it open the signal EP wave. All right, I'm going to get the signals. I'm going to choose this because it's the thing I'm testing right now, and I'm going to pin these selected signals. And it goes through a 0 and then 1, and B goes through twice as fast, and C goes through even faster, and this gives you the output F. All right, so cool. That's what shows up there. If I wanted to run a different simulation, I would comment out that first one. Let's do the top. Okay, save that, run it. Get the signals. Okay, I want the top here, and I just need these signals. Sorry. I just want this one. I keep pressing the wrong button. This one and this one. All right, and so this is the reason I use this vector notation for the inputs, because this now shows me the list in terms of the decimal equivalent of the binary combination. So 0, 1, 2, 3, 4, 5, 6, 7, and you can look at the output F for each of these combinations. All right, so in the first case, the select line is 0, and in the second case, the select line is 1. So you can use your ERT table to look to see if F out is correct for these cases. Okay. So at this point, if you see this, everything's working, you're ready to move to the next stage. The next stage is to click on the download the files after the run. It's going to send that to a zip file, and you can copy all those files to your box space under a sources directory, and you'll be ready to go with Vivado. All right, so that will be the subject of our next video, is how to push things into Vivado and look at the test benches. All right.